Today we're going to be doing some more Calculus 2 practice problems, focusing on integration by parts. So integration by parts is just a product rule for integral. We already have a product rule for derivatives. Obviously we learned that at the beginning of Calculus 1, but now we have a product rule for integrals, where if two functions, u and dv, are multiplied, let's see, if we have u, we can find a du, and if we have v, we can find, if we have dv, we can find a v. We're going to use all four of those in this equation, uv minus the integral of v du. So the answer to this integral is going to result in another integral, but usually that second integral will be a lot easier to solve. So let's look at examples of identifying what these u and dv terms is. It's not always so simple as like u and dv, right? Well, actually in this case it is. U is always going to be the like polynomial term, because we want to break that down through one, two, or more integration by parts, as we'll see in a later example. And then our du would just be dx. And we like to make dv something that's easy to integrate. That ends up being super easy to integrate, right? Because if you were to take the derivative of 1/9 e to the 9x, you get an extra 9 from the chain rule, which would cancel with the 1/9, so we know we did that correct. So we're going to use all four of these in the formula uv minus the integral of v du. And then that integral will no longer have a product in it. So let's look at this one. What we're going to do in this case is make this entire thing u. It doesn't make sense to have ln x in any dv because we don't know how to integrate ln, or not yet anyway. So u is going to be that, and that means dv is just dx, which is fine. dv can just be dx. With integration by parts, we're able to solve some integrals that we're not used to be able to do, like arctan, where of course we're going to take the derivative of it and integrate that derivative to get back to arctan like we did in the last video. But now we can actually integrate arctan, and we can actually integrate ln of x dx by using integration by parts. So let's look at some examples. These say to find the indefinite integral. So let's look at this. U is going to be that polynomial term, in this case just x. dv is going to be whatever's left, right? So that means du is just dx, and v is the integral of cosecant squared x, so that works out good. It's just negative cotangent x. That should be on your formula sheet if you don't have it memorized. So we know this is going to turn into uv minus the integral of v du. So let's see, u is x, v is negative cotangent x, minus the integral of v du. And v was negative cotangent x, du is just dx. So we knocked down the power, this x to the power of 1, we knocked it down 1 by doing one round of integration by parts. And you'll see on this next one, we're going to have to do 2. So let's see, what is the integral of, well, first let's cancel out these negatives to make it positive. What's the integral of cotangent? Well, assuming you don't have that one on your formula sheet, it's a pretty easy integral. Now we have a positive integral of just cosine x over sine x. So we can do a substitution, u equal to sine x. That means du is going to be equal to cosine x dx. And now we have a integral of du over u, right, which we know turns into the natural log of the absolute value of u. So finally, it's negative x cotangent x plus the natural log of the absolute value of u, which is sine x. So now we're able to evaluate integrals with a product in them. But they can get a bit harder. They can get a bit harder when now we have to do it more than once. So if we call u equal to x squared and dv equal to e to the 2x dx, that means du is 2x dx, and d, or v, is 1/2 e to the 2x. So now this integral is going to turn into, I'll start it down here, uv, or x squared over 2e to the 2x, minus the integral of v times du, right? So the 1/2 and the 2 cancel, and now we're left with another product, so we're going to have to do another integration by parts. And since we started with u being, I'll write it off to the side. Since we started with u being the quadratic term, we're going to continue that by making u equal to now x, du is going to be dx, dv is going to be e to the 2x, v is going to be the integral of that 1/2 e to the 2x. There's also a dx with dv. So now x squared over 2 e to the 2x minus, but we're subtracting off that integral, but that integral turns into two terms, uv, x over 2 e to the 2x, minus the integral of v du, right? So this is a mistake a lot of students make, is they don't distribute this negative to this term as well. So we're going to make sure to do that. This becomes x squared over 2 e to the 2x minus x over 2 e to the 2x plus the integral of 1/2 e to the 2x, which is just 1/4 e to the 2x, because an extra 1/2 is brought out. And of course the plus c. So one place where students definitely make the most mistakes in integration by parts is when you have 3 or 4 integration by parts. If your instructor is not being nice to you, then they will lose track of the negatives. So keep track of the negatives by having organized work. Okay, let's look at this one now. See, now, like I mentioned earlier, we're able to solve this integral. If we call this u, we can just call dx dv, and we'll see what happens. U is equal to arctan of x. Du is equal to, what's the derivative of arctan of x? It's dx over 1 plus x squared. And dv is dx, which means v is x. So don't get too scared off by this, because it's going to work out perfectly. This is going to turn into or uv, which is x arctan x, minus the integral of v times du. See, now this is a much easier integral, like I mentioned earlier. We can just do a u sub for the bottom, and du is 2x. Good thing we have an x and a dx up here, because now that makes the integral much easier. Let's put the 2 there and account for it with a 1/2 out front. Now we have the entire du on top. So let's see, this turns into x arctan x minus 1/2. What is the integral of du over u? It's ln of u, or the absolute value of u, 1 plus x squared, plus c. Finally, minus 1/2 ln. We can drop the absolute value sign, because x squared plus 1 will never be negative. That graph does not drop below the x-axis. So we can simplify it a little bit. So now we can look at some more integrals. One called the parts wraparound problem. See, in this case, there's no good u. And what I mean by that is that when we take the du, it's not going to really get us closer to an easier integral, because both this trig function and this exponential function have unlimited derivatives and integrals, so there's really no good u or dv substitution. So just pick one. What would you rather take the derivative or integral of? I would rather derive a trig function, because integrating that e to the x will be super easy, but integrating trig, we can sometimes get it mixed up with deriving. So du is the derivative of cosine negative sine, and v is the integral v to the x e to the x. Right, so this is going to turn into, and what I'm going to do here is I'm going to put an I. I is going to represent the answer. Okay, so I equals uv cosine x e to the x minus the integral of v times du. And the negatives cancel. I like to keep track of the negatives. And with this equation, we're going to keep u as our trig term, sine x. So du is cosine x dx. And dv is once again e to the x dx. So v is just e to the x. Now this integral right here, let's see, I is equal to cosine x e to the x plus uv sine e to the x sine x minus the integral of v du, which is e to the x cosine x dx. Does this integral right here look familiar to you? It's what we started with. That's why we call it a parts wraparound problem. And we had already said that that integral is equal to I, right? So now we have I equaling cosine x e to the x plus e to the x sine x minus I. So a little bit of algebra here. We can add the I to the other side. 2I equals cosine x plus sine x. Factor out the e to the x to finally get I equals 1/2 e to the x out of sine x plus cosine x. So a cool algebra trick right there with plugging in that function for I will prevent us from doing infinity amount of integrals, right? So the final answer is 1/2 e to the x out of sine x plus cosine x. That is the parts wraparound problem. Finally, we want to look at another general solution of a differential equation. We had looked at this, we had looked into this when we first started with u substitution. This is just scratching the surface of the differential equations. But now we can do it with ln x, right? So the trick to these was rewriting y prime as dy over dx and multiplying both sides by dx. Now we can integrate both sides. Integral of dy, integral of ln x dx. So y equals, let's see, we're going to call this u and this dv. So u is equal to ln x, du is equal to 1 over x dx, dv is equal to dx, and v is equal to x. So this integral turns into uv, which is x ln x, minus the integral of v du, which is x times 1 over x dx. So now these x's cancel, and we're just integrating 1 with respect to x. So y equals x ln x minus x. And then we have that c because it is a general equation, right? So that is our final answer. If you were to take the derivative of this function, you would get ln x. And that is how we use integration by parts.